So, Mr. Haas, I grew up in Appleton, Wisconsin.
Did you?
I did.
Really?
And when I lived there, it had about 50,000 people.
I'm going to write this down.
I think you should.
All right. I think this is going to be an exponential problem, I'm thinking.
Yeah, it started at 50,000 people when I was there, and it actually is growing at about 1% annually. So let's write an exponential.
So 1%, that means 100% of the people plus an additional 1%. 101%, I move the decimal two
And
places
it's
over.
going up every year.
Okay.
Yeah, very nice.
Well, I happen to grow up in New Paltz, right here.
I've heard of that
Right here.
place.
Actually, I went to high school at New Paltz High School.
Very cool.
Yeah. There was about 10,000 people then.
Okay.
And at the time, it was growing rather rapidly. I would say it was probably growing at around 3% a year.
Wow, pretty impressive.
There we go.
Very nice.
So what are you thinking, Miss Stewart?
I'm thinking there might be a time when the population of Appleton could equal the population of New Paltz if
Write that
these
down.
rates of growth continue, because New Paltz is growing faster.
So you want to know, this sounds like a good problem.
It does.
You want to know when the population of Appleton is going to be the same as the population of New Paltz, because New Paltz is growing faster.
Yes.
Little equation there.
Little equation, set them equal. I bet we could solve this.
I think I can probably divide by 10,000 initially.
Very nice.
Simplify it a little bit. Divide this side by 10,000. And so if I divide 50,000 by 10,000, that's going to be 5 conveniently. 1.01 to the x equals 1.03 to the x.
Very nice.
This is a little weird because I have two things to the x. I'm going to take the log of both sides at this point.
Yeah.
You could do it, there's a couple of ways to do it here, but this is kind of how I like to do it, if that's all right. I mean,
Let's do it. Let's take the log of both sides.
So to take the log of, this is something students sometimes mess up. I'm taking the log of something times something. Log of a, b. Remember that rule?
I do.
Log of a times b is the log of a, in this case 5, plus the log of b.
Very nice.
Log of b, which is this whole thing, 1.01 to the x.
Very nice.
By the way, the other thing sometimes students do is they'll bring this x down in front of the whole thing. Don't do that.
Yeah, no.
This is the guy raised to the x.
Yeah, only the 1.01 is
Of
raised
course.
to the x.
So I'm taking the log of the other side. That is 1.03 to the x.
Looking good?
Thank you very much. I mean, now I can do this little log maneuver where I bring them both down, and let's see.
You can go down below there.
One
That
more
looks
step. Okay.
good.
So log 5 plus x log 1.01 equals x log 1.03.
Very nice.
I'm solving for x. I'm going to move all my x's to one side.
Fantastic.
So let's see. Can I maybe erase a little bit of this stuff?
Sure.
I'm going to erase this business here, but I think it's still
Yeah. Gives you a little more room.
okay. So
Very nice.
I'm going to move all my x's to one side, so I have log 5, and I'm moving this guy, so that is x log 1.03 minus x log 1.01. You know, we do this maneuver a lot. I'm solving for x. Hey, everybody with an x, go to one side,
Yeah.
and then what do?
I factor.
You factor out an x.
Because you can't really combine those nicely. You could with your calculator, but let's factor out an x.
That's, I mean, every time. Everybody with an x go to one side and then factor out the x.
Absolutely.
Log 1.01, I factored out the x.
Now can I just hurl that in my calculator?
Absolutely. It's really just going to be, I'm going to divide both sides by this whole huge long thing. Basically,
Yeah.
this is going to end up underneath my log 5, so I'm going to write the whole thing here. It's
Fantastic.
log 5 divided by this whole thing, log 1.03 minus log 1.01.
Drum roll, please. I'm
And what do you
putting that
have?
whole thing in, and if I round to the nearest year, it's actually 82 years.
In 82 years,
That's really
New
remarkable.
Paltz will be the same size, and which is kind of amazing because think about it, that doesn't mean that New Paltz is going to be 50,000 in population. It's going to be whatever Appleton is, which is also growing.
Right.
So that's not nothing.
That's not nothing. Of course, that assumes that these rates are going to continue for 82
Right,
years,
absolutely.
which probably will not be the case.
Well, we'll wait and see, because
We
I'm sure
will-
we'll both be working here.
That's right. We will be.
This is another exponential function. Actually, you have two of them that you've set equal to each other. Now, one is growing using the continuous. Oh, it's
Right.
e to the something. And the other is 1,200. Now, that could represent anything. It's like $1,200, making 2%, 2 times a year.
2 times a
Okay,
year.
we want to know when these amounts are equal.
Right. So I'm going to solve it. I'm going to use logs. I think since that e is there, I'm going to use natural log just because that's handy, but it doesn't matter. I could use log base 10, log base e, whatever I want. But I'm going to use natural log because natural logs are nice. Let's clean things up a little bit first. I'm just going to divide both sides by 60 just so I have fewer numbers hanging out. So I have e to the x. Let's see, that gives me 20. Did I do that
That is
correctly?
20, you are correct.
Very nice. 1.02 raised to the 2x. All right, that's a little neater. Should I just go ahead and take the natural log of both
Absolutely.
sides? All right, I'm doing it.
So now you could use log, but
I
you're
could
going to
use log
use
base 10.
ln. It's the same. You'll get the same answer.
Same answer, absolutely. I like using the natural log because the natural log of e, of course, is 1. So it's just one less thing for me to put in the calculator. So I'm just going to take the natural log of both sides. Now, remember, Mr. Haas, you reminded them of this, taking the natural log of something times something. And remember, logs are exponents, so when you're multiplying exponents, you add the exponents. I didn't say that right, but you know what I mean. So this is going to be the natural log of 20 plus the natural log of 1.02 raised to the 2x. Are we okay so far?
Looks good.
I'm going to bring those down. When you raise an exponent to another power, you multiply the exponents, right? Natural log of 20 is going to hang out. That 2x is coming down. And again, the 2x is only affecting 1.02 because that's the only thing being raised to that exponent. All right, let's see. I'm solving for x, so let's find here's an x term, here's an x term. So I'm going to subtract this from both sides. I'm bringing my x's over to one side, right? Isn't this what we usually like to do?
Looks good.
All right, so let me just write this out. X. Do I have to write the natural log of e?
Well, ln of e is just 1, and if you forget, you can, of course, just punch it in your calculator.
Yeah,
but
so are we okay with my just writing
Absolutely.
x at this point? Okay. Minus 2x times the natural log of 1.02 equals the natural log of 20. Okay, I can't really combine those nicely, but I could factor out an x. So let's factor out an x. Of course, I'm left here with a 1, that's the natural log of e, minus a 2 times the natural log of 1.02. All equal to natural log of 20. Hey, I'm so close. All I have to do now to get x by itself is to divide both sides by that big thing. Do a little magic in my calculator. You make me feel like a natural log. All right. Does this make you feel like a natural log, Mr. House?
Absolutely.
Are you putting that in the calculator for me?
I am.
Oh, you're fabulous.
So, Ellen, you want it all in just one shot there?
One kitten caboodle,
So
one
I
shot.
get 3.11927. I guess that's probably
That's
enough.
probably
So
enough.
why don't you call, yeah, you want to round it to 4 places?
Why not? 3.1193. So if I'm talking years, it would take about 3 years for those two quantities to be equal to each other, or whatever.